Bismillahirrahmanirrahim. Assalamu alaikum dear students. This is our third lecture for second week for the course of wireless and mobile communication systems. Uh, in our previous lectures in this week, we talked about the cellular systems and we discussed that this cellular architecture, it enables us to reuse the frequencies over and over again in order to provide an overall gain in the capacity of the system. So basically this cellular architecture is adopted so that we can increase the overall capacity and serve more users with the limited spectrum. In today's lecture, we are going to talk about some related concepts related to the cellular architecture, and first thing that I'm going to talk about is the effect of clustering and this frequency allocation on overall system capacity. As we have already discussed that the main objective is to increase the capacity of the system. So how much increase is possible through this proper frequency allocation? So let us assume a very simple scenario. Let us say we have a total frequency band or our available spectrum for a particular cellular system of bHz. So like some governmental agency has allocated a specific band of bHz that we want to use to deploy our system. Of course, we have to divide the total band B into smaller channels, and we need to have duplex communication in wireless system. So each communication or each user would be required to have two channels. So if we have the bandwidth of half duplex channel is W hertz, in that case the total number of duplex channels that will be available for use in this particular type of system will be B, which is actually total number of available channels, total available bandwidth which is allocated from governmental bodies, and divided by 2W, which is actually the bandwidth required to establish full duplex communication. Let us denote the total number of full duplex channel by S. So S represents the total available channel in our system. Now if we want to use the cellular system, we have to divide these total available channel among different cells. So for each cell, how many different cells need to be allocated different frequencies, that depends on the cluster size. So if we have a cluster size of n cells, so we need to divide this channel into n cells. For the time being, we assume that we are distributing the channels in equal proportion. So each cell gets equal number of channels. Although it's not practically possible in every case, and sometimes we intentionally change the number of channels in different cells to meet the requirements of users, but for the theoretical point of view, we can make a convenient assumption that all the channels are equally divided among different cells. So let's say for a cell we have allocated a number of channel which is denoted by K. Of course K will be smaller number as S, because the S number of channel are to be distributed among n different cells. So each cell will be having K channels, which will be S divided by n, where S represents the total number of available channels and n is the number of cells in the cluster. And of course, as we have already discussed in our previous lecture, that frequency reuse factor for this particular case will be 1 over n, because we will be using 1 over n of total number of channel in a cell. Okay, so once we have distributed all the frequencies, all the channels in different clusters, so how many total users can be accommodated in that particular region? This is the big question, because the number of users that we can serve in a specific region is actually related to the capacity of the system. So if you want to increase the capacity of the system, we need to increase the number of possible users in that particular area. As we have already discussed that once we have made a cluster, in order to cover the entire region, we repeat that cluster several times in order to cover the entire region. So let us assume that the cluster is replicated m times. So m represents the number of times the cluster is replicated to cover entire region. So the total number of full duplex channels that can be obtained in this particular scenario are given by this expression. C is equal to m, which is total number of in which the number of clusters has been repeated in that particular area. K is number of channels associated with one cell, and n is number of cells in a cluster. Alternatively, we can represent this this total number of full duplex channel to be m multiplied by s, where s is the number of channels in one single cluster and m represents the number of times the cluster has been replicated. So you can see that we this total number of channel, it actually depends on this number m, because if we increase the number m, eventually that will end up with a proportional increase in the capacity of the cellular system. So primarily you can see that the number m determines that how much increase we can get from the capacity. One may expect that an increase with k and n, but it does not actually make a significant change, because if you see from the previous expression, k is actually inversely related to the n. If n is increased, k will decrease, so eventually they cancel out their effect. So increasing k or n does not make any difference in the capacity. The only number which is significant in this expression is m, which actually represent how much increase we can get from replicating the channel in this particular scenario. So you can see that if we reduce the cluster size n, provided that the cell size is kept constant, do not change the cell size, that means we will be required to more clusters to cover the given region. Eventually, if we are using more clusters to cover a region, eventually it will lead to a large value of m, and having a large value of m would result in more capacity of the system, because that will give you a larger value of c. However, you should note that if we are reducing the cluster size n, in that case co-channels will be moving closer and closer, and eventually if you are having a close co-channels, eventually they will introduce interference into the other co-channels. So basically this increase in capacity is at the cost of higher interference because of the shorter distance between co-channels. The reverse is also true. If we increase the cluster size n, keeping cell size constant, eventually we'll be having lesser number of clusters and to cover the entire region, and eventually we'll end up with the smaller value of m, and we'll be having a smaller capacity of that system. But the advantage in that particular case would be, because of the larger cluster size, there will be larger distance between two different co-channels, and eventually you will be having lesser interference from co-channels. So basically it's a trade-off. If we intend to increase the capacity, we end up with the interference problem, and if we try to reduce interference, eventually we have to compromise on the capacity. So when we are designing a system, so we have to be considerate about these two aspects: how much capacity we need and how much interference level we can tolerate. From design point of view, because we want to have more capacity in the system, so it is desirable to have a smaller value of n, because when we reduce the size of n, eventually it leads to the increase in a capacity. In order to maximize the value of C, we need to use a smaller value of n, but we should note that we should not go to the very small value that leads to higher interference. So we have a constraint in that case, that we want to minimize the interference as well. So we have to choose between a specific value that gives a desirable capacity as well as limits the interference to the acceptable range. Okay, second important thing that I want to discuss in this lecture is channel assignment strategies, because when we have made a cellular architecture, we need to assign channels to different cells in the system. There are actually two types of channel assignment strategies. First one is known as fixed channel assignment. In case of fixed channel assignment, each cell is allocated a predetermined set of voice channels. So out of the total allocated voice channels, some specific number of channels are allocated to the cell. If a user attempts to make a call in that particular cell, so that the base station picks a channel from the already assigned or allocated voice channels and establish the call. If all the channels in that particular cell are occupied and a call attempt is made, in that case the call will be blocked and subscriber will not get any service. So basically the base station has the control over the allocation of the channel to any user or any subscriber, because the channels are dedicated to that particular base station. This strategy is relatively very simple and requires very less amount of processing, but it has a drawback that it has higher probability of blocking. Once all the channels get occupied, a new call attempt cannot be entertained. In order to improve the performance of such system, sometimes some other strategies are used. For example, one strategy is named as borrowing strategy. In borrowing strategy, a cell is allowed to borrow channels from a neighboring cell if all of its own channels are already occupied. So if all channels are occupied and a new call attempt is made, the base station will request the MSC to borrow a channel from a neighboring cell, and MSC will check the neighboring cell if a channel is available for use by that particular user. So eventually MSC will allocate that particular channel to the base station, and the call may be successful. In this particular case, the MSC or mobile switching center has to supervise the borrowing procedure. Second type of channel assignment is actually called dynamic channel assignment. In dynamic channel assignment, voice channels are not allocated to different cells permanently. So all the channels are basically controlled by the mobile switching center MSC. Each time a call request is made, the serving base station has to request the MSC to allocate a channel. The MSC once it gets a request for channel allocation, it has some algorithm that runs at the background. This algorithm takes into account different types of cost functions in order to minimize the errors and problems in the systems. For example, these cost functions are likelihood of fixture blocking within the cell, the frequency of use of the candidate channel, the reuse distance of the channels, and so that and so on. So these are some of the cost function that are that affect the algorithm, and eventually on the basis of this cost function the algorithm is run at the MSC, and MSC makes a decision to allocate a new channel to the requesting base station. The MSC only allocates a frequency if it is not presently in use with the cell or in any of the nearby cells, because the most important parameter is to avoid co-channel interference. So MSC has to take care that if a frequency is already in use, it should not be reallocated to any nearby cell. The important thing regarding dynamic channel assignment is that the MSC has to collect the real-time data. There are various types of data that are being maintained by the MSC in order to plan for the channel allocation. This real-time data include different parameters such as channel occupancy, traffic distribution in the region, and radio signal strength indications RSSI of all channels on a continuous basis. So basically MSC gets this data for all possible channels in that region and has to make a decision on the basis of all such data. Eventually, because MSC will be making lots of computation in determining the channels to be allocated to entertain a call request, it increases the storage as well as the computational load on the system. But the biggest advantage in such dynamic channel assignment is that the channels are better utilized, and the probability of call blocking gets decreased, because if a certain cell has more users in particular region, so the more channel will be diverted towards that particular cell, and if a cell has lesser number of users, the lesser channels will be allocated in that particular region. Eventually the overall quality of service from the user perspective would be increased. Okay, third thing that we want to discuss in today's lecture is handoff. Handoff is a very important aspect of cellular communication system, because when the user is mobile, especially if they are moving with the high speed, maybe in a vehicle or something, if there is a probability that a user moves from coverage region of one cell into another cell. If this happens, for example, a mobile moves into a different cell while it's on the call, conversation is in progress, so there is need to transfer the call from one base station to a new base station, or there is a need to transfer the call from one cell to another cell. This transfer of call from one base station to another is named as handoff. Handoff operation not only involves a new base station but also requires that the voice and control signals be allocated to channel associated with the new base station, because we want to transfer the entire conversation from the old base station to the new one, which will be the new serving station for the mobile user. In many implementations, generally handoff is prioritized over the call initiation request when a new channel is allocated. For example, in a particular cell there is only one available channel, and that's the cell receives a call of handoff, as well as the cell receives a call initiation request. In that case, the base station will be prioritizing the handoff, and it will entertain the handoff request and that drop the new call request. Handoff has to be performed successfully and infrequently as possible, because handoff also causes burden over the system. So we intend to have as minimum handoff as possible in our system. And secondly, the system has to complete the handoff in such a way that user does not perceive any interruption in the service. So it should be imperceptible to the user. How this handoff is maintained? Actually, there is a threshold defined by the system designer. An optimum signal level is defined at which the handoff is initiated between two different users. It must be noted that in wireless systems there may be some deep feeding occurring even if there is no need of handoff. So in order to avoid handoff on the basis of momentarily signal loss or momentary fading, we have to the base station has to monitor the signal over a certain period of time. If signal remains at low level for that certain period of time, in that case the handoff is initiated. Otherwise, if that signal loss is due to fading, it will recover within the shorter period of time. So basically, whenever this signal strength goes below the optimum threshold level, in that case the handoff is initiated. It is very important to properly choose a threshold. If threshold is not properly selected, in that case there will be a problem in the system. For example, if a threshold is too low, in that case the base stations and mobile switching center, they would not get sufficient time to transfer the call from one base station to other. In that case, the call may be dropped due to low power level before the handoff is completed. So it can be problematic if we choose a very low threshold. On the other hand, if threshold is kept very high, in that case it will cause unnecessary burden on the system, because whenever that threshold is passed, eventually the base station would initiate the handoff request, and if with a high threshold, there will be more number of handoff requests which are not needed in that particular scenario. So in order to avoid unnecessary handoffs, the threshold should be properly selected. Sometimes it happens that MSC starts handoff procedure. For example, a mobile is moving from the coverage region of a cell into the coverage region of another cell, and MSC initiates the handoff procedure, but the new cell does not have any free channel. In that case, the MSC may have to wait for some time, or maybe if there is heavy traffic loading, it may require additional computation. In that case, if it takes a longer time and call level goes beyond the acceptable limit, in that case the call may be dropped without completing handoff. So there are few scenarios where handoff may not complete properly, but in most cases, as I said before, that most of the system, they prioritize handoff, so most of the cases handoff is achieved successfully. This is a graphical illustration how the handoff is completed. For example, we have two base stations, base station 1 and base station 2 represented here, and a mobile unit is moving from base station coverage region of base station 1 to base station 2. As the mobile station is moving towards base station 2, it has to pass through this boundary. Before this boundary, for example, this level A, the signal level would have dropped to a sufficiently low level. For example, let us take the first case, for example, the represented by a figure, which is representing the improper handoff situation. That means the handoff is not performed, or due to some reason handoff is not completed. What happens? As the mobile user goes beyond this coverage region of this base station 1, the power level would be dropped rapidly. So at level A, this is the power level. If we move further, the power level goes to another lower level at which the handoff is initiated. This is the handoff threshold. So the base station has to initiate the handoff request. If the base station does not initiate the request, or due to some reason the handoff request is not contained, the power level keeps on dropping. Eventually it ends up at some point which is the minimum level for the acceptable level for the signal, the base station to maintain the call. As soon as the signal level goes below this minimum acceptable signal level, the call is dropped. So the call would be dropped before the handoff is complete. If we have a proper handoff situation, like represented here in figure B, so what happens? As the mobile user crosses the point A, the signal level is at this point, and as it goes towards base station number 2, the signal power level goes down and down and down, and when the handoff threshold is achieved, the base station initiates the handoff request, and after processing, the base station would hand off the communication to the base station number 2. Eventually, once the base station 2 take up the call, so the signal level that are available with base station 2, that will appear at the mobile station. So at B and beyond, you will be getting the signals from base station 2, and as the mobile unit is moving towards the base station, the signal level will start increasing. In this way, the handoff is properly completed, and the call is transferred to the base station number 2. Okay. While talking in terms of handoff, there are certain terms. One of the important parameter is known as dwell time. Dwell time is actually random time, but it gives the statistics of a call in a particular cell. So we define dwell time as the time over which a call may be maintained within a cell without handoff. This is called dwell time. Alternatively, dwell time is defined as the dwell time is the time that an active call is maintained within a cell without handing it off to another cell or dropping it. So this statistics of dwell time is actually very important for handoff planning purposes, because it gives you an intimation after how much time a handoff request has to be initiated by the base station. Typically, the statistics of dwell time they depend on the speed of the user as well as the type of radio coverage. So this dwell time generally is incorporated in the handoff algorithms so that the proper handoff is achieved without dropping the call. Okay, second important thing regarding handoff is that there is a planning need to be done at the back end in order to successfully complete the handoff. In first generation phones, the base station and MSC used to collect the received signal strength indicators data, RSSI data, so that they can plan and identify the users who are in need of handoff. However, this scenario became different in second generation and all the later generation. In second generation, the handoff decision is now mobile assisted. We generally call it mobile assisted handoff or MAHO. Mobile assisted handoff is a new approach towards planning of handoff. In mobile assisted handoffs, the mobile station, they has to measure the received power from all the surrounding base stations. So any mobile station who is in a call, they keep on tracking the received power from all the base station and reports these measurements to the serving base stations. In this particular case, the base station keeps on comparing the power level with itself and all other base stations that are being reported by the mobile stations. If in certain point the received power level of the serving base station becomes lower than any other neighboring cell, in that case the base station initiates a handoff request. So basically the handoff request is initiated on the basis of data provided by the mobile station. When the mobile station reports that another base station is providing more power as compared to the serving base station for a certain period of time, eventually the base station initiates the handoff request so that the handoff is completed without any interruption in the call. This mobile assisted handoff is actually very helpful in many circumstances, because the mobile station handoff they remove burden from the system, because in mobile assistant handoff the data is basically gathered by the mobile station, and the mobile switching center MSC, it does not have to constantly monitor all the signal strengths. So this MAHO handoff, they require lesser computation at the MSC site as compared to the general handoff that we discussed before. Secondly, MAHO handoffs, they are done at relatively faster rates. So eventually these handoffs become more suitable for microcellular environment where the user need a frequent handoff. Okay, so sometimes it happens that a mobile moves from a coverage region of one type of cellular system into coverage region of another cellular system. So basically a mobile moves from a coverage of one of the MSC into a different MSC region. In that case, a handoff need to be made between these two different types of systems. So this type of handoff is named as inter-system handoff. So inter-system handoff becomes necessary whenever MSC can no longer find any base station or any cell within its own coverage to provide services to a particular user. So whenever the signal becomes very weak in a cell which is adjacent to some other system, and MSC is unable to determine any other cell in particular system, so eventually it will request handoff to another different system so that the call is transferred to that particular system. This inter-system handoff, although it is important to provide continuous coverage, but it is associated with different types of issues. First of all, because MSCs and different systems, they are designed with a particular setup, and their internal setup may differ with each other, so there can be a compatibility issues between two different types of MSCs. So before making an handoff, a compatibility need to be determined. Secondly, it may be possible that a local user may become a roaming user. So a local call may be converted to a long distance call with that incur higher costs. Similarly, the different systems, they have different policies and methods to manage handoff requests that may hinder this inter-system handoff. Okay, as I discussed before, we want in many systems we want to prioritize handoff. Some of the systems, they do not prioritize handoff. They handle handoff request in the same way that they handle new call requests. In that particular case, the handoff request will only be served as long as there is a free channel in that particular cell, and the blocking probability in that particular case would be same as the blocking probability of incoming signal. But from user point of view, it makes lots of difference. Think about yourself. What is more annoying? If you are trying to make a call and it does not goes through, or you are in middle of a conversation and call abruptly drops. So call dropping is more frustrating as compared to the call failure. So basically, from user point of view, it is very important to have a proper handoff rather than entertaining a new call request. In order to improve the quality of service, most of the system, they prioritize handoff requests. In order to prioritize handoff requests, there are different strategies that are being used by different systems. Two of the strategies are we are going to discuss here. First one is called guard channel request, and second is queuing of handoff request. The guard channel concept for prioritizing handoff is based on the condition that some of the channels in a particular cell, they are reserved for handoff and they are not used for initiating a new call. So if few channels, they are reserved whenever a handoff request is used, but when a handoff becomes necessary in that particular cell, eventually the cell will use one of the reserved channel as long as the reserved channel is available. Even if all the reserved channels are already used by other users and a handoff request is achieved, and there is another free channel which is not reserved, even in that case the cell will entertain the handoff request, so using one of its other remaining channels. But if all the channels, including all the reserved channels, they are fully occupied, in that case handoff will fail and call will be dropped. However, there is one drawback with the guard channel concept, is that because we have reserved few channels for handoff, the overall system capacity is reduced, because if all other channels are occupied and reserved channels are free, even in that case new call request will not be entertained. In order to optimize that thing, we use a queuing of handoff request. In this strategy, once the received signal drops below the handoff threshold, a handoff request is initiated. If a channel is available, the handoff is completed, but if the handoff is not available, the call is queued and it remains associated with the original base station, and handoff is not initiated, and the system waits for any channel to become available. As soon as a channel becomes available, the call is transferred to the new base station. But eventually, if it takes longer time and call goes the signal goes below the minimum acceptable limit, the call would be dropped and handoff may not be completed. So this queuing of handoff request is actually important in the sense that it improves the overall system capacity, but there is a certain probability that handoff may not complete if the channels become occupied for the larger amount of time. So this concludes our discussion regarding the handoffs. So in today's lecture we talked about the system capacity, then frequency assignment allocation strategies in different channels, and third thing that we have discussed in today's lecture is handoff. So we'll stop here for today's lecture. We'll continue the related topic in next week's lecture. Thank you all.